What's going on, everyone? So today we're going to be talking about the covariant derivative. For just a note to all of my American viewers, hope you had a happy Thanksgiving. Now let's get right into the topic, but before we do that, make sure to hit that like and subscribe button. And now let's get into the topic. Also make sure to hit up that Patreon page if this is the kind of content that you enjoy watching. Anyways, so let's get into the topic. So we are now going to dive into the covariant derivative. We're going to spend a few videos talking about this very, very important mathematical object because it's going to be sort of the stepping stone to getting really deep into other different types of derivatives like the exterior derivative and the Lie derivative. But anyways, when we came across the covariant derivative initially, this is what we had found. We had found that this object here was a covariant derivative, and that was equal to a regular derivative of some vector. This is a vector at some space, at some point in spacetime, plus some difference between the parallel transported vector and the vector at a new spacetime point. So you can imagine as spacetime is evolving, vectors are moving within that spacetime, and the covariant derivative tells us exactly how vectors stay the same within that spacetime in some sense, because we're trying to track this notion of parallelism. Pictorially speaking, we can imagine flat space. If you're looking up in flat space, you have a vector looking upwards like this. If you move in the direction x mu, dx mu, right? So this is actually going to be the direction of dx mu. If you move in that direction, then say towards over here. So imagine we're just moving this direction in. This is the direction of dx mu. And this is the vector we're looking upwards. Well, we're still going to be looking upwards in flat space. Okay. And in this case, there is no difference between the parallel these two vectors. They're both parallel transported across flat space. There's no difference, so the covariant derivative is going to be 0. In curved space, however, the story is a little bit different. Suppose we're always looking up, right? So in the previous video, we always want to say you're always orienting your head upwards, okay, and you're always looking up towards the heavens or whatever. But if you're walking on a curved space and you're always looking up, well, in one case you're going to be looking in this direction. If you're over here, then you're going to be looking off in this direction. So with respect to this vector, this direction's not up, right? This is like slightly off to the side, or you could think of it as sort of subtending by some angle, right? So this vector is not the same as this vector, but we could say it's the same if we take into account this blue difference right here, right? So if we're looking up here, we're looking in this direction. So there's a difference between these two vectors, okay? And that difference is this blue vector, and the covariant derivative is going to give us something that represents that blue vector, okay? So we can think of the covariant. So we want to think first, we're going to sort of take the abstract approach to this covariant derivative first, and then we're going to get into some more concrete examples later on. We can think of the covariant derivative as a map that takes in 3 objects to output a single number, okay? And the 3 objects are going to be alpha, x, and gamma, okay? Alpha is part of the covariant space, or the covariant vectors, or covector space. X is part of again, these are all tangent spaces. X is part of the tangent space on the manifold, and not U. Sorry, this is gamma. Gamma is going to be part of the tangent space as well. So we have one object part of the cotangent space. Really, this object right here is really the thing that's going to drive everything to a number, right? Because the definition we're going to put in here is this object, when you put in three things, well, this object, if it's applied to just these two guys who are in the not the covariant space. This is going to give us our covariant derivative. And so when our covariant derivative is sandwiched in with a covector, we get a number. Okay, that's going to be the idea here. So when we feed in, for example, when we feed in a vector and a covector, we're going to get an object that looks like this, and this is a rank 1, 0 tensor, right? In other words, this is a vector. And so what brings a rank 1, 0 tensor to a number? Well, a rank 0, 1 tensor. That's the object that was in this space. If we leave these two guys open, however, this object is only fed in this object. This is a rank 1, 1 tensor, so we need an object going in here and an object going in here to bring this to a number, right? And so this here is considered a rank 1, 1 tensor when we're not specifying a direction of travel. Okay, I'm going to go up here really quick. So here's our visual schematic that we've sort of been modifying and building on. So we have our vector space. It has a basis. We have its associated covector space, and we can get from here to here through the metric. We found a relationship between the metric and the affine connection. We found how the affine connection is related to coefficients of acceleration vectors of these guys. That was the extrinsic geometry. Again, the intrinsic geometry was when we related the affine connection to the metric. Okay? And so now the picture that we're putting here is, okay, well, here's our affine connection. We found out that if we feed in a couple of objects to the affine connection, well, what we get is something that looks like this. This is that difference. This is that difference. This is that difference, or the object that contained all the notion of parallelism. So the object that contained all the notion of parallelism is given by this. If we feed in this object to here and this object into here. Okay. Now the indices don't really match, right? If I made them match, then this guy would be a mu, or actually, so I have a mu summing over here. This guy would then have to be a gamma, right? So this guy would have to be a gamma, and so we get, that's what this, so these guys again would give us that notion of parallelism. Now we have this idea of a covector. A covector, we now have said is a rank, this is a rank 1, 0 tensor. And so we can build this object by feeding in our vector, okay, and by feeding in the direction of travel again, right? Because we need to feed the direction of travel and the vector to get the covector. And by doing that, right, so this is going to be gamma. We're traveling in the gamma direction, right here. The output of this guy is going to be our complete covariant derivative, right? Because we said that the definition of this was this. Right, so this is this visual schematic that we're looking at. And we've talked about the covariant derivative as being a map, and this is going to help us for later when we're going to talk about using the covariant derivative of tensors. So this means that the covariant derivative has a basis. If it's a rank 1, 0 tensor, well, its basis is going to look like this. And you can replace the basis again with our realization. E alpha, we said through our realization was that, and E upper alpha through our realization was this. And so we can replace the basis. We're going to do that later. This is just easier shorthand to keep things looking a little bit nicer, I think. And so but so given that this is a covariant derivative and it has a basis, so we could also theoretically conceive of a contravariant derivative. A contravariant derivative is sort of the opposite of a covariant derivative, right? It takes the basis here is going to be this guy as opposed to this guy, right? So I'll take this guy here and just bring it down here. Okay. So we have a notion of a covariant and a contravariant derivative. Now let's take, what I want to do in the sort of last part of this is, now that we have this knowledge of covariant derivatives as being maps, we want to take this idea and we want to apply it to a tensor. We want to ask ourselves, what is the covariant derivative of a tensor? So we've thought of these things as being maps. So we input something like this. Again, we need to input this guy here. So this is our vector. This is our covector. Okay. So we need to input something else. Well, initially we were talking about inputting a vector. Okay. But now let's input a tensor. And the type of tensor, just as an example, you can do this with any tensor you want. With any tensor. What you can do is, what we're going to do is we're going to pick a rank 2, 0 tensor, okay? We're going to see how this prescription works really nice. We'll realize that this prescription actually works really nice in keeping everything, realizing something about how tensors, how we can take the derivative, covariant derivative of tensors. But anyways, this is going to be our tensor. Okay, it's a V. It makes it seem like it's a vector, but this is going to be a tensor. Here's that definition, and here's the component notation for this tensor. And we have this tensor product. We need the tensor product because we're dealing with tensors again. And so we can move the tensor product over, and now we want to take a look at this. So if we take a look at this guy, we're going to apply the derivative to our components. Then we want to apply the derivative to the basis vectors. And so that's what we're doing right here. Okay. And then we go from this step to this step. Well, we realize that the connection, remember the connection coefficient we said was the derivative of the basis vectors. That was something we've said early on also. And so we can replace that with, so here, outlining in red, is this. And then this is this guy right here. So we've just replaced this with our connections, and then we take the basis vectors out, right? So here, so we have E alpha, E beta. We want this guy to be an E alpha, and we want this guy to be an E beta. So we have dummy indices that we can switch around. So we're going to change this to an alpha, so which helps us change this to an alpha. So we change these two guys to an alpha. We want to change these two guys to a beta, so that's going to be a beta. These are all just dummy indices, right? Because we don't have, we don't have mu's, right? We don't have mu's on the side, so these things are summed over. So these are dummy indices. Mu's are dummy indices. Right, so we can change them, and we can also, so if we're changing them, we have to change these guys, the alphas to mu's, right? So mu's to alphas, alphas to mu's, mu's to betas, betas, and then betas to mu's, right? So mu right here. And so what we get is something that looks like this, and then it's fairly easy to see that this looks like this is the covariant derivative of these are the components of the covariant derivative of our rank 2, 0 tensor. Now you can do this, right? You can do this entire procedure with, say, a rank 3-1 tensor or a rank 4-0 tensor. And you could see exactly how the coefficients are going to look when we take that derivative. But what's even more interesting is that, okay, well, this is our covariant derivative. Or this actually isn't quite our covariant derivative, right? Because we need to apply this guy now, right? So when we apply that guy, he shows up right in here. Okay? So this is the covariant derivative or rank 2 0 tensor, right? So we can think of this. So we can think of this now as, okay, this object, right? This object here. If we can input, what we need to do is that, well, the first thing we need to do is say, okay, if this is a rank, this thing here is a rank 2, whoops, a rank 2 0 tensor. Not a rank 2 0 tensor, right? This is actually a rank 2 1 tensor, right? Because we have a lower index now. We add that's why this is called the covariant derivative. We add an index to that covariant portion of the rank. And so, okay, so if that's a rank 2 1 tensor, we can write its components as alpha, beta, gamma. Okay. So we can say that the coefficients are going to look like this. Okay, these are these coefficients right here. So those coefficients, well, what is this thing has to take in a vector. Well, so this can take in a vector. It can take in also two covectors. Okay, so in order for this guy, this object, to spit out a number in the context of a rank 2 tensor, or rank 2 0 tensor, what we need is we need to input our rank 2 0 tensor, right? So we need a space for a rank 2 0 tensor. We need a space for our alpha, or our A. We need a space for our B. We need a space for our C. And then these also have bases, right? So it needs to take in a vector, and a vector. So this thing is actually taking in a lot of stuff. So it needs to take in these things, it needs to take in these things, and it needs to take in the coefficient, or the tensors also. Right, so what we're going to get is 1, 2, 3, 1, 2, 3. Right, so it's going to take in, it needs to know the dx direction, it needs to know d alpha, it needs to know del beta, it needs to take in gamma, beta alpha, C alpha, and then, our tensor, which was our rank 2 1 tensor. Alright, so this was a lot, right? Because when you go back here, the thing that drives this object to this object right here to a number is whatever we put in here. So that's where these guys are coming from. Okay, so this object needs to take in a lot to spit out a number. But anyways, so this was practice for a rank 2 0 tensor. So this thing is therefore a rank 2 1 tensor, where this was a rank 2 0 tensor. So we've increased this value by 1. And you can imagine now doing this for, say, an object like this. try practice for yourself and see what you get. And ultimately, ultimately how I like to think of this is, again, building on the architecture of space-time. I'm not going to draw it out again, but you have vectors, you have connections now, we have metrics, we have now a covariant derivative. And all of this is really making sense, right? Because it's telling us how different objects move, how everything is related to one another on this smooth manifold, and how this four-dimensional smooth manifold evolves in time as well. But anyways, with that being said, I hope you enjoy this kind of content. Make sure to hit that like and subscribe button, and I will see you guys in the next video. Bye.